Right, we move now to Colin Snodgrass, Dr. Colin Snodgrass from the Open University, who is going to talk about It Came from Outer Space. And I'm not going to give the second half of the title because it involves a Hawaiian word that I struggle with, but you'll tell us how to pronounce it correctly.
Yes, so I'm going to tell you a little bit about Oumuamua, which is this interstellar object that was discovered late last year and has caused us lots of entertainment, lots of interest. And especially because there's a lovely picture like this, which was from the ESO press office, that inspired lots of people who want to believe to think that this was aliens. So Oumuamua. This was discovered in October of last year by the Pan-STARRS survey in Hawaii. This is why it has a Hawaiian name. And immediately its orbit appeared to be unusual. It appeared to be hyperbolic, and this was confirmed a week or so later, and the discovery was announced. And at this point, it was given a comet designation, because we think of things on very eccentric orbits that tend to be comets. It passed perihelion, quarter of an AU, in early September, and it passed relatively close to Earth, which is why we spotted it. But it was already outbound from the sun and getting fainter at the time that it was discovered and that we saw it. This is what its orbit looks like compared with, so you've got the planets orbiting in a nice disk. This is a sort of typical comet orbit of a Halley type. It might be Halley, I don't know which one they picked. And this is Oumuamua. And you see it came in from way out of the plane, swung around the sun, and then disappeared again. And this, from the zoom in here, shows you its path, that it came close to the sun, and it came close to the Earth, and then we spotted it as it reached the night sky, going outbound beyond the Earth, and then we could observe it. But we could only observe it for a very short period of time, so people scrambled like mad to get telescopes on this thing, because it's the first time that, we've been predicting interstellar objects for a long time, but it's the first conclusive interstellar object, or macroscopic interstellar object we've seen. And so we got most major facilities around the world. People phoned up and begged and wrote DDT proposals and got their friends who were on the telescope to take observations for them. And the reason we had to do this really quickly is that this thing was going very fast, and its brightness was evolving quickly. And what I'm showing here is, so this is dates through last year, from July to December, second half last year. On this axis, distances, so this is distance from the sun on the red line, and it comes to perihelion. This is distance from the Earth in the green line. And then these combine to give you how bright this thing is, which is in V magnitudes on this scale. And you can see this is where it was discovered, where it happened to be closest to the Earth and its brightest. And it was still about just a bit brighter than 20th magnitude in V. So this is still pretty faint. This is what it looked like in the discovery image from Pan-STARRS. It's this faint streak here. So this was, hard to discover and already faint, and then fading pretty fast. And so this is when it was discovered. It had already faded by quite a bit by the time it was announced. So in the week it took them to confirm the orbit and announce the thing, already it was a couple of magnitudes fainter. So, and getting much fainter. And we couldn't have seen it over there where it got briefly bright before, because that's when it was behind the sun. So this is the only time it was in the nighttime sky and we had any chance. And then we had an extra challenge, which is that now it's announced and it's already fading. That's when the moon was in the way and we couldn't observe it. So we had literally a few days between it being announced to when the moon got too close to observe it. And by the time it was out the moon again, it faded another couple of magnitudes. So, by then it's down at 24th and you're needing some big bits of glass. So, yeah, there was a bit of a scramble. But we got lots of telescopes on it. This is showing when we got observations. So these are the discovery images, this is confirmation, this is where it was announced. And these are dates through from 18th of October through to 1st of November. So, this is really, you can see days here, you can see when it's getting dark at different places on the world because of when we start observing it. And you can see all of a sudden it's announced here, and then lots of telescopes start piling in. Palomar is on it that night because Joe Masiero was checking his email while observing and saw the announcement and went, that sounds more interesting than what I'm meant to be doing, I'll have a look at that. And then the rest of us that had to write proposals were on it 24 hours later, and then the next night, and you can see, so there's this mad rush to get on this thing. And that's basically all we got in a week. So everything else follows is based on this sort of week's worth of data. There are a couple of other observations made with HST and Spitzer, because it took a little bit longer to swing them in the right direction, that were a few weeks later. But everything we got from the ground basically was in that first few days. Now, the interesting thing is, if you look on this scale, is then you start plotting when these results start coming out. And this is where papers appeared on Archive. And this might not be as remarkable to people who work in extragalactic physics, but Archive is very, people in solar system astronomy are very bad at using Archive. And half the time we don't even put our papers on there when they are accepted. And then mostly we only ever put accepted papers on there. But for a while we got to have fun and pretend we were extragalactic astronomers and put papers on as soon as we got the observations and submitted them. And you can see, so this is the first paper on Archive. This is from Maciero, the guy that was at the telescope when it was announced. The paper was on Archive before most of us had even got onto the sky. With the first spectrum. And then, these are all then observational results following. And then this is the publication of the first published paper in Nature a couple of weeks later. So there was a bit of a frantic rush. This is a list of the papers that appeared on Archive up until December. There are more than this now. There's a whole lot in there. There are a few interesting highlights, like proposing a mission to chase it down, and whether or not it can be macroscopic dark matter, which is an interesting question. But mostly observational results and some modeling results of where does this thing come from, what does it tell you about planet formation. But the first thing that we sort of get from the observational results is that this thing looks like an asteroid. This is the faint dot in the middle. This is Oumuamua. These are star trails because we're tracking the object moving. And this is a bit of a surprise because you expected something coming in with this, it was given a comet designation, it was on this comet-like orbit. We expected interstellar objects to be comet-like because most of the stuff that's thrown out of solar systems as they form is thrown out from the outer parts and is icy. And so you expected something that's made of ice that comes to within a quarter AU of the sun to give us a lovely comet tail. And it didn't. So what the next thing is we get a spectrum of it. Now, these are spectra taken with the WHT, the red points, and the VLT and X-shooter are the grey points. And these are nice in that they go out into the infrared a little way. And what is overlaid with this are typical asteroid-type spectra. And so you can see it looks quite like a solar system asteroid, one of the primitive types. Like a D-type asteroid is a reasonably good match to it. The thing's got a red slope in the visible range and slightly more neutral slope in the near infrared. So it looks like an asteroid from this point of view. But you can also overlay the icy bodies of the solar system and what their typical spectra look like. And you see that you also get a pretty good match with things that look like Trojans or comets. It's not as red as some of the more outer solar system objects, centaurs and Kuiper belt objects, but it's a pretty good match for sort of icy surface things like cometary nuclei or Trojan asteroids. So what else can we learn about it? Well, the other thing that people did was get light curves of it and measure sizes and shapes. This is a little sketch. This is how you can get some idea of the shape of an object from measuring its light curve, just measuring the brightness change. This is a model of Itokawa, and as it rotates, the surface area changes. And if you measure the brightness, you get something like that. And so from just measuring the brightness and how that changes, you can get some idea of the shape. And from some idea of the shape, you can get some idea of the density or the internal structure. And you can get some color measurements to complement the spectra. And this was the paper that was published from Karamich. There were a few other light curve papers first, but this is the most comprehensive one that came out in this first Nature paper, because Karamich was part of the team that discovered this, so they had a head start. And they had this nice light curve over a few nights, and you get this clear rotation, and it has a period that's somewhere in 7 to 8 hours. But the thing that's remarkable is that the amplitude of this light curve is very high. There's sort of 2.5 magnitude range between its faintest and brightest point, which also made it quite difficult for the observations. But what this turns out, if you look at that range, that implies that the actual ratio between the shortest and the longest axis is this 10. This is where we get this idea that it's a very elongated body from these light curve measurements. And to put that in context, this is a histogram of known asteroid shapes and the axial ratio of those, and you see most of them are sort of, 1.5 or so. The most elongated asteroid we know in our own solar system, Cerberus here, is sort of 5.8, and that's what the shape of that thing looks like from light curve models. That's pretty elongated. And then Oumuamua from these light curves is somewhere out here. So that's when that, this is where this press image comes from with the release of that Nature paper. And immediately you can look at that, and if you spent too much of your youth, as I did, playing X-Wing versus TIE Fighter, you know exactly what that is. This is a Rebel cruiser, and very good match. So, this got lots of people very excited about, this is aliens and all these wonderful things. I said, it's quite surprising, though. The studies we had on before we discovered this, and what we expect to see is we would expect that the first interstellar object we discovered would be an icy thing. Firstly, because we expect there are more icy objects in the interstellar space, because you eject more icy objects, and also because it's a lot easier to discover a comet than it is an asteroid for the same size, because its activity will give it a bright coma and tails. This is going a little step backwards, why we think it's more likely that you get icy objects. This is a sketch of our current favourite model of the formation of the solar system, with this Grand Tack and Nice models, where you start with rocky things in the inner part of the disk and icy things further away. And as the giant planets form and migrate, they scatter material out, but they preferentially scatter things that are icy, that are out in the outer belt where they're forming. The other way that you get interstellar objects is that they're released from the Oort cloud. So the Oort cloud is relatively loosely bound. Passing stars can steal our Oort cloud objects away and liberate them into interstellar space. But again, most of the Oort cloud is icy, so you'd expect those to be icy objects as well. So can it be icy? That's the question that we wanted to ask. So we expect it to be icy. The spectrum is consistent with an icy object, but we didn't have any activity. And this is where we started doing some work at the Open University, and this was work that was done by Ben Rositas, looking at the thermal behavior of this thing. Comets have very low thermal inertia. The heat wave from the surface of a comet passing inwards goes very slowly. And this thing went past the sun really quickly and then disappeared again. So it went very close to the sun, but it wasn't there very long. And this is the result of the modeling that Ben did. So you can see the surface temperature gets quite nice and toasty above 500 Kelvin, but you only have to go a little way down in the surface for it doesn't get as warm. And actually, below sort of 30 centimeters or so, the temperature never actually rises to the point where you'd get sublimation of ice. And further down than that, it doesn't even rise to the point where you would have more volatile ices. So one interpretation of this is if you've got an insulating layer, if you've got a surface layer that doesn't have any volatile ice on it, on the object, then the fact that it has this low thermal inertia means that will have never seen the heat of the sun and can prevent it having activity even if it's got ice on the inside. One other interesting idea is that because it rises slower is that possibly this thing would have some outburst and you'd see activity much later. But it faded beyond where we could follow it before you get to those predictions. So the lack of activity doesn't actually rule out subsurface ice. This thing could be icy or so. Thermal models predict that actually you will have a sort of devolatilized layer on things that have had long period of cosmic ray bombardment that's up to a couple of meters deep, so easily deep enough to give you a layer on it. But can it still be icy? Can you have something that's this elongated shape that's just supported by ice? I mean, some of the press reports of this thing were, it must be made of metal if it's so elongated to support it. That's not true, but it helps the alien idea. Actually, you only need a strength of a few pascals to support the strength of this thing if you're using tensile strength to hold it together, which is comparable with the measurements from Rosetta for comet strengths. I mean, it's a strength of pile of talcum powder. It's really not a lot. But it is compatible with what we have for comets. It has some interesting implications for the Oort cloud and for comets, because this thing is very small. It's smaller than most known comets. And Oort cloud comets have also been out basically in the same environment as interstellar space in terms of bombardment from cosmic rays. So if this thing's been devolatilized and doesn't have any activity, why do comets from the Oort cloud, when they come in, show these beautiful tails? And it could be that there's some size effect, and actually there should be a large population of things on Oort cloud comet orbits that will never show activity. Mostly they're very small and hard to discover, but we could expect to find some in the future. And then the other question is whether or not this elongation is really the case, because one of the other, the interpretation that the light curve tells you it's really elongated is based on the light curve being entirely due to shape. That the maximum is when you see it side on, the minimum is when you see it end on. But you can get the same light curve with something that's round that happens to have a white spot on one side and a dark spot on the other side. And so there is this idea, that, and you do see this on larger objects in the solar system, that there's this question of, is it shape or is it albedo? I have another model that demonstrates this very nicely. These are the two different models you get of this. So this is from Luke Dones. I can't take credit for the joke, but it's too good, so I had to include it. So yeah, you can have something that's basically the same color all over, but very elongated will give you this light curve, and you can also have something that's black on one side and white on the other. Can that be the case? Well, if we look at these two spectra that we had from the WHT and from VLT, you can see there are subtle differences. So maybe it's redder on one side than it is on the other. So we went to go and try and investigate this. And to do that, what we did is we collected all of the data that all these various people have taken. And this is work that Wes Fraser's led, and don't tweet this stuff because it's embargoed until Sunday, when it will appear. But what happens when you take all of the data that various people have got over this week and then try and put it together and phase it and see where is one side red or not, is one side darker than the other, is you discover that actually the reason why different authors publishing them within a week of each other all had slightly different rotation periods is because you can't fit one simple rotation period. You can't phase all the data into one period. This thing must be tumbling through space, so its light curve is a complex shape. That's interesting because that firstly means that it doesn't have to be as elongated to explain this. If the tumbling explains some of the odd shape of it, you can get differences between minima and maxima without having the shape being so elongated. But also, we could then look at the measurements of the different colors that were measured, and you can see that where we measured it to be redder corresponds with sort of some peaks in this light curve, and where we measured it to be less red corresponds to where there are some minima. And then this is difficult to do because we can't phase all of it because of the tumbling model. But there's certainly an indication that you can explain some of it with having some albedo variation as well as some shape. Assuming that the difference in color leads to a difference in albedo, which is a reasonable assumption but not guaranteed. So the model you get from this then suggests that actually you can explain this with, it's still elongated, it's still an axial ratio of 5, it's about as elongated as anything we've seen in the solar system, but it's no longer twice as elongated as anything we've ever seen before. The tumbling interpretation tells you something else in that it probably tells you a bit about the internal structure. Because if you leave something in space that's tumbling, eventually it will damp to a simple rotation. And this hasn't, so that tells you a little bit about its lifetime. Doesn't give you a very good constraint because it just tells you that it's younger than the age of the universe, which we probably already knew. But there is another nice thing, because someone else pointed out that actually it's another argument against it being a spaceship. Because if it's a hollow thing, the damping timescale's a lot less. If it's got moving parts, the timescale's a lot less to damp it down. So that does probably rule out that it's a spaceship, which is unfortunate because people quite like that idea. Also, they did try listening to it with a radio telescope to see if it was talking to us. They also didn't get anything. So again, if it's a spaceship, they're smart enough not to be talking to us. But this does allow us to put this all together and give us another idea of what this thing looks like and another model, which is that it's not quite as elongated as it was before. It's tumbling through space. It can be red on the sides, but with a more neutral color on the top and the bottom. And that means I can find another spaceship that I can model this with, which is this one. So it's possible that this has come from some extrasolar Elon Musk with great ambitions. So anyway, in summary, this is it's been a great fun adventure that we've had following up this first discovery of an interstellar object. Its surface properties actually look quite like things from our own solar system, from icy bodies from the outer solar system. It could still be an icy object without activity because you have this thermal model that can suggest the ice can be buried under a layer. If that's the case, then it has implications for comets in our own solar system. We should expect the LSST in particular to find lots of small comet objects on orbits that come from our own Oort cloud that are also devolatilized and don't show activity. There's also a lot of implications for planet formation. There's a whole bunch of models that have looked at the rate at which you would get things scattered out and what that can tell you about planet formation process. So far, with n equals 1 data points, there's a lot more different options in the models, but we expect n to get a lot bigger than 1 relatively soon, because with LSST, we expect to start finding things like Oumuamua at about the rate of 1 a year. So we're entering an era where we can actually study small objects from other solar systems on a fairly regular basis. And with that, I'll stop and take the questions. Thank you.
Thank you very much, Colin. Fascinating presentation. Okay, we have a few minutes. Chris.
Hey, thanks. If the suggestion is that it has red sides, how does that make it unusual in our solar system, or do we see small bodies with that sort of variation?
It would be unusual for something that size. Well, I mean, we don't have that much data on things this size, but in our solar system, we know of some objects where you see changes in albedo, like Pluto, for example. It's got this sort of, the white part on one side and the dark red side on another. But that's a much bigger object. In terms of small bodies, asteroids and comets or nuclei, there isn't convincing evidence for things that have this kind of difference in albedo across the surface. So that it is interesting in itself. Why should it have that pattern? That is an open question.
The comet that went into Jupiter many moons ago split up into about 10 or 20 bits, I think. Could this be an object that split up into 3, 4, or 5 pieces?
There was a talk in the specialist meeting we had earlier, very much on that suggestion that it could be that this is a fragment of some larger object, and that's how you get the kind of elongated shape that it's passed close to something, being kind of stretched and spaghettified and smashed from a larger piece, but then escaped. You have to the dynamic model saying that this is possible. The question, of course, is with Shoemaker-Levy 9 going to Jupiter, it was spread out, but it was spread out by that point it was doomed. It was going to crash into Jupiter. It wasn't then spread out and then escaped. But my understanding is this is possible, and if Dimitri, this is around somewhere still, he can talk more about that, because there was talks about that in the specialist meeting. So it is possible, yes.
Very quick, Colin. How big did you say it was?
A couple of 100 meters long is was thought. It's not that we're waiting for the Spectra data to give us an albedo and a better idea of the size, but assuming sort of normal asteroid or comet type albedos, it's hundreds of meters long. It's a pretty small object. That's why it's so faint and difficult to spot.
Let me ask a question, if I may. Now that we've seen this strange object, is there any possibility that, observing strategies or data analysis techniques will change, and now that we know that the one such object exists, is it likely that because of that we will find more?
Well, I think what will increase the chance of finding more is more just the improvement of technology of surveys. So, I mean, we found this thing now that Pan-STARRS is quite good at finding moving objects, and Pan-STARRS has been quite good at finding moving objects for a few years, and we found one. And Pan-STARRS has now been upgraded with a better camera, and then LSST will come, and that will increase the rate. But what would certainly be nice to get is discovering one of these things inbound, so we get a chance to look at it before it goes past the sun. That would be what we would like to spot next. But yes.
Okay. Well, thank you very much indeed, Colin.